С этой стороны, с какой стороны?
Слева все.
Слева все? Стараюсь немножко завернуть. Да, сам стул будет все равно плохо видно. Давайте сделаем, чтобы эти две целиком были, а слева тоже видим.
Давайте.
Давайте попробуем сделать так, чтобы здесь вот это было.
Сейчас.
А там какая получится. Да, теперь нормально.
Короче, тогда теперь видно вот эту, вот эти две.
Вот эти две просто, да?
Да, но это чуть-чуть там в конце
Ну,
обрезать.
чуть-чуть на конце ничего, я не буду совсем туда залезать.
Я сейчас очерчу, чтобы он был.
Вроде так.
Ну да, примерно.
Нам еще не пора. Да, без конфей, не знаю. идет и запись. Чуть-чуть. Раз. Идет, кажется, да, хорошо. Надеюсь, я ничего
Ну, я
не знаю.
проверял, он...
Так, ну давай герой. Да, давайте потом. Перерыв. Well, let's start. The previous lecture, to the very end of the previous lecture, I described a construction of chart classes. It was very quick and without details, so first we start with somewhat more careful construction and some of their properties. But let us start with general definition. What is a characteristic class? And generally, what is a characteristic class? There are characteristic classes for different versions of bundles. So first of all, we need to fix a class of bundles with which we work. For instance, we can consider k-dimensional, n-dimensional vector bundles, or n-dimensional real bundles, or some bundles, fiber bundles with particular fiber. There are many versions. In each situation, characteristic classes is a natural way to assign to each bundle a homology class of a base. So assume that for each bundle we have associated, let it be E, associated class A of E in the homology of the base. Again, different versions of cohomology. We deal with Dirac cohomology, but one can consider singular cohomology and so on, with different coefficients. So there are many versions. One should fix class of bundles and cohomology theory. Cohomology theory can be even some extraordinary cohomology theory, such as co-bodies or K-theory, everything. So but in our consideration, of course, Dirac homology. And the only property which we would like to have is naturality. So if we have a map, again, in our situation, smooth map of smooth manifolds, but in singular situation, continuous map of topological spaces, so again, different versions. But actually here there is no difference. The matter is that any map of smooth manifolds can be approximated by smooth. So then we have, if this is F, we have induced vector bundle. There is standard construction over each point. We have the fiber over its image. And then the only property which we would like to have is this property. So this is naturality, and well, why this is a useful notion, and why homology but not homology? We could write down something like that in homology. Nothing interesting. The matter is most important reason why it is interesting in cohomology and not interesting in homology is that there are a lot of theorems like that. For instance, I will not prove them, but I hope you at least hear about them. If you would like to study complex vector bundles over some base M, then they are in one-to-one correspondence with maps from this M to some classification space. Namely, here we have Grassmannian of n-dimensional space, complex Riemannian of n-dimensional subspaces in C infinity. Actually, the reason is easier that any such bundle, at least over a complex M, can be embedded into as a sub-bundle of a trivial bundle, and then we get such map. Then over each point, one have a subspace of Cn. So this should be thought about as limit of this. So this one is just direct limit of this where n capital goes to infinity. So there are properties like that. It is not so important that it is Grassmannian, it is just important that there is such a space. There is such a space that, say, vector bundles, and for different types of bundles, there are other types of spaces called classified space. So why this is nice? This is nice since characteristic classes are just, I don't want to prove it exactly. So these brackets means homotopy classes of maps, but characteristic classes are in one-to-one correspondence with cohomology classes of this guy. Why? If we have homology class like that, then for each vector bundle we obtain a map from M to here, and we can take pullback of this A along this classifying map. And we get a homology class of M, and certainly we have this naturality. And actually vice versa, over this guy, over this space, we have universal vector bundle, just tautological vector bundle, and its characteristic classes are well defined. This is not so well defined in de Rham situation, namely this is an infinite dimensional manifold, and we do not have de Rham homologies. So this is not a. I suggest that we look at this not as on a theorem which I have proved, but on some philosophy, which is why it is useful. But in our situation, I will just construct certain characteristic classes of complex vector bundles explicitly. These classes are called Chern classes, and before I defined them, I have defined them on the last lecture, but it was too quick and without details. Before I define them in details, I would like to list their properties. Well, when we deal with vector bundles, then there is one more important property. If this A of E satisfies this property, then we say that we have a characteristic class. But there is one more important property. If we have, in addition, it, then we say that we have a stable characteristic class. This property is like that. If we have a bundle, then we always can form a bundle with fiber of dimension n+1 just by adding a trivial bundle. We have such stabilization. And assume that we have a characteristic class not only for n-dimensional bundle. Well, no. We have Cn here, we add one more C, and we have Cn plus 1 here. Assume that in addition, we have the following property, that the characteristic class must be the same. The characteristic class must be defined for bundles of all dimensions, and it doesn't change when we add a trivial bundle. So trivial bundles doesn't matter. Then, if we have both these properties, then we have a stable characteristic class. This is just a definition. And so first of all, these shared classes, yes, first of all, these are classes of complex vector bundles. Classes of complex vector bundles. First of all, we have a series of classes numbered by positive integers, and ck of E lives in 2k dimensional cohomology of the base, of course. In our situation, it will be Dirac cohomology. In fact, a deeper result is that everything can be repeated in singular cohomology with integral coefficients. So actually, it is important that these shared classes are integral cohomology classes, but in fact, some integrality, some part of integrality properties we will see even on Dirac level, but not all. But in our consideration, so these, when we pass from singular cohomology to Dirac cohomology, then we lose some information. For instance, we lose torsion completely. So these are real shared classes, not integral. Well, and first of all, we would like that the property is that they are stable characteristic classes. This means that we have this naturality for each of them, and we have this stability. Okay. Second property is that ck of E equals 0 whenever k is less, k is greater than dimension E. So if we try to compute the 100th shared class of 10-dimensional bundle, then it's always 0. And also, we have already one characteristic class. We know already one characteristic class. This is Euler class. Euler class is non-stable. In fact, Euler class will be denoted by E of E, yes, and we have defined it for an arbitrary oriented real vector bundle, yes. But it is not a single characteristic class. Namely, in fact, it is a series of characteristic classes. A Euler characteristic class of 10-dimensional bundles has nothing with Euler characteristic classes of 4-dimensional bundles. They live in different gradients. So we do not have, we of course do not have these stability properties. And so Euler class is non-stable. We have this naturality property, but not stability. So this Euler class is non-stable.
A question?
Yeah.
So by dimension of E, you mean the dimension of C vector space in the fiber?
Yes. Dimension of it is sometimes called rank of E.
Okay.
Yes. And rank over C. It is important. Yes. Let's better say that it is rank. I mean, of course, is the dimension of the fiber, and the dimension of the fiber is complex vector.
I have a question about stable characteristic
Yes.
classes. Can we describe them using crucified spaces, so taking the limit of Tasmania and
This is precisely that. Yes. Okay. Now, but again, as we say about the rank homology, we have no good rank homology in this situation. They need to deal with other homology theories. And if what happens if we have A equal to rank? Then this is just the Euler class. look, they live in the same dimension. If Euler class exists for oriented real bundles, and it lives in, if you have an oriented real bundle of some rank, then it lives in this particular dimension, equal to the rank. If E is a complex vector bundle, then it is a real vector bundle of rank twice as much. Yes, and exactly Euler class lives in two cases of homology. So at least this formula, I haven't proved this yet, but at least they live in the same homology. Third property is so-called Cartan's formula. This is a very nice formula explaining how to compute Chern classes of direct sum of two bundles if we know Chern classes of sums. We need to take the sum over all partitions of K into two, all the compositions in the sum of two non-negative integers. And this is CE of E, CG of F, but we need here a convention that C0 is always 1 in zero-dimensional homology. And actually, it is convenient to rewrite this formula in the following way. It is convenient to introduce so-called full Chern class of bundle, which is just a formal sum, 1 plus C1 of E plus C2 of E plus and so on. We always deal with finite dimensional vector, finite dimensional manifolds, so of course the sum is always finite in the cases interesting for us. But if we start to work with singular homology spaces like that, then it can be infinite. But in our situation, so it's finite. This is a cohomology class of the base, but non-homogeneous, inhomogeneous cohomology class. It lives in direct sum of homologies of various dimensions, homology group of various dimensions. And then this formula can be easily rewritten in the following form: that full Chern class of direct sum is just the product of full Chern classes of sums. And of course, if we open brackets, then we get exactly this. So this is the same. Yes, that's almost all interesting properties. Almost all interesting properties. And actually, now let us. There will be one more interesting property, but the blackboard finished, and I will formulate it later. Yes. So now let us repeat in detail the construction. Actually, I wrote an incorrect sign in one place on the previous lecture, so it is one more reason to repeat it. So, first of all, theory that characteristic classes satisfy these properties exist and are unique. Almost. No, with these properties completely. So, characteristic classes satisfying these properties exist and are unique. And actually, first I give construction, we check properties, and then we see why it is unique. So construction. I have already said it last time, but now let us repeat. Assume that we have a bundle with fiber Cn, vector bundle with fiber Cn over a manifold. Then we can consider an associated, the projectivization of this bundle, the associated bundle, fiber bundle with fiber, the projectivization of the fiber of this bundle. So this is a bundle, but I would like to write it in horizontal direction. Fiber here is Cpn minus 1, and this is called projectivization of E. And this point is F. In details, what is the associated bundle? In fact, this bundle is glued out of such charts, yes, along some partially defined on the intersections. This is a part of usual. I don't want to go in further details, but this is a part of usual definition of bundles. We have such charts, and we have this Gaifullin cycle, which we have some matrices at each point x of base, at each point x in the intersection of two charts, we have this Gaifullin cycles which lives in J and C, yes, and we identify point x and C in chart alpha. We identify with point x and G alpha beta of x V in, well, something like that. Actually, it is better to do it vice versa. Okay, and we do it for all alpha and beta, and we have this cycle. And the matter is that this projectivization is glued using the same cycle, but now instead of vector, we have a vector up to proportionality. We have Cpn minus 1. And starting from the same cycle, we do this fiber bundle. What is important? Important is that here we have the, if this is denoted by F, then here we have the pullback of E. And now, what is a pullback of E? Pullback of E is by definition, how the pullback of a vector bundle is defined. It is a subset of Y, say S in E of E times E, such that they agree under these projections, such that phi of Y equals phi of S. Yes? And this is exactly as to say that the fiber over each point Y is the fiber of this bundle over P of Y. Well, but look, what is a point Y here? A point Y is a pair, a point in the base, and a line in the fiber. Well, this is just projectivization. This is a point in the base and line in the fiber of this point. So A is a line, a one-dimensional subspace in the fiber of E over X. And now look, over this Y we have the same fiber EX. So we have a prescribed line in this space. So if we are here, then all lines in EX are equally matched. There is no distinguished. But if we choose a point Y, then we choose a prescribed line in the in the fiber EX. So here we have letters denoted by Xi. We have a one-dimensional. This is Cn, but here we have only C. Xi is a one-dimensional tautological bundle. Tautological bundle means that fiber of Xi is exactly a point here is XL, and this L is exactly the fiber of Xi over this point YA. This Xi is naturally a subbundle of this induced bundle. Well, and here the point where I have a wrong sign. We can consider two things. First of all, we can take the Euler class of Xi, of tautological bundle Xi, of Euler class of Xi, and this one lives in two-dimensional homology of P of P. Well, the matrix Xi is bundled over here. It is oriented since it's complex. Then when we think of it as of real, then it is oriented. So we have this well-defined X, and we have got the following. Actually, it is more convenient to take X not to E of Xi, but to minus E of Xi. And this is exactly what we did last time. Last time we said that I would like to consider not tautological vector bundle, but dual of tautological vector bundle. So we can consider eta, which is the dual bundle of Xi. We always consider dual vector space instead of. In other way, this is, look, in each bundle we can introduce Hermitian scalar product. And then dual is automatically isomorphic to conjugate vector bundle. So this is the same as to say that this is conjugate vector bundle. This means that we consider the same vector bundle, but conjugate the operation of multiplication by complex numbers. Each time we would like to multiply by E, we multiply by minus I instead of it. Then of course, if we go to real bundles and we forget about complex structure, then they become the same but with opposite orientations. So of course we have this X is just E of eta. And we have already discussed that if we take the restriction of this X to the fiber, what is the fiber? Fiber is Cpn minus 1. Then we get the dual of a tautological vector bundle just over Cpn minus 1. And we have calculated a lot about Cpn minus 1, and finally we understood that the two-dimensional form which we have written for several times standard form is exactly the shared class of the bundle dual to the topological one, and this is exactly the generator of two-dimensional cohomology of Cpn-1. And moreover, this is the generator which is the Poincare dual to Cpn-2 and Cpn-1. We have discussed this. The matter is that when we go to fiber, we can completely forget about E. We just have Cpn-1, and we have the dual of topological vector bundle. We can understand how the Euler class of it is organized. It is organized like that. It is important to have here minus, or we have minus here. So to have plus here, we should have minus here. But well, I think I erase these properties. But now the place where I wrote a correct sign on the last lecture. Now what we have? We have that we know that the homology of this Cpn-1, the homology of the fiber, we have computed them, and this is the truncated polynomial ring. Let us denote this generator by U. Yes? This is generator of cohomology of Cpn-1, and we have just truncated polynomial ring u to the n here. Yes? U to the n equals 0, and up to dimension we have just a polynomial ring. And in particular, this means that, look, if we take additive basis here is 1, u, and so on, un minus 1. This is an additive basis of cohomology. And we are exactly in the condition and in the situation of the Ray-Hirsch theorem, which I formulated and discussed last time. So we have classes 1, x, and so on, xn minus 1. These are classes of this. We would like to apply the Ray-Hirsch theorem to this horizontal vector bundle. Horizontal just in my notation. We have these classes which, being restricted to the fiber, give additive basis in its cohomology. Then the Ray-Hirsch theorem says that the cohomology of P of E is a free module over cohomology of the base with basis 1, x, and so on, xn minus 1. And then x, but this Ray-Hirsch says only on the structure of a module. It doesn't say anything about how the multiplication here is organized. So it is by no means true in general that x to the power n is 0. There is no reason to think that it is 0. But what we know, we can raise x to the power n, and it lives in a free h star of a module with these coefficients. This means that we can write c x to the power n as a linear combination of these classes with coefficients from the homology ring of the base. And this is where the sign was incorrect. A correct sign is like that. I would like to write it like that. all signs are pluses here. Well, where these Ci of E are those classes from H star of M, but by dimensional reasons, they must live in H2I of M. And there are unique such classes. We would like to write Xn, we could put it to the right hand side. So Xn is uniquely written as a linear combination of 1, 2, and so on, Xn and minus 1, with coefficients from the base. So, here multiplication means the, what does this multiplication mean? This is the action of H star of M on H star of P of E. So to be completely accurate, we should add here F star of this. We should raise it to there. So this equality defines completely these classes. I'm sorry for on the previous lecture I wrote here minus, plus, minus, plus, and so on. This is because I remembered that I should add minus in one place. Either we should add minus here, or we should alternate signs here. I forget and I do both things. This is indirect. So we could write plus here, and we could write minus plus here. And this is the same. But if we wrote minus here, then this is like that. Okay, what do we see from this? What do we see from this definition? First of all, of course, this is a natural construction. If we have another a map from some M star, from some M prime here to M, and then we can get the pullback of the whole picture to here, and of course we have naturality. So of course these Ci are characteristic classes. But up to now, look, we have separate definition for bundles of each dimension. They are not related to each other. So at the moment we cannot say that this is their stable characteristic class. We can say this, but we cannot prove it at the moment. So what we know? We know that these are characteristic classes, and actually we look for n-dimensional bundle. We define only C1, C2, Cn. We do not have any higher classes. Just by definition. By definition, we put Ci of E equals 0 when E is greater than rank of E. So this property is just by definition. Well, but now we would like to understand what we still need to check. We would like to check stability. We would like to check that the higher Euler class coincides with the higher Chern class coincides with the Euler class, and we would like to check Cartan's formula. The easiest and the most important thing is Cartan's formula, though it looks like it is the hardest one. And first we prove the Cartan's formula and then understand everything. But let us start with one remark. The first remark, let us look on this definition when E is just linear bundle. Linear means that it has rank 1. So what happens in the situation when E is just linear bundle? So in the situation n equals to 1. Everything is trivial. What is the projectization of a linear bundle? look, over each point, it's just M.
Yeah.
Yes? We have only one line in each in each fiber. So this is just M. This is just identity. Identity map. Here is E, and here is again E. We have one-dimensional subbundle. The only is one-dimensional subbundle of one-dimensional bundle. So all these are E. All these is identity. So in fact, what we say that we take E itself. And look, and what is this? What is this? This says us that we have X plus. We cannot write this X star, of course, since it's we just arrive at such equation. Yes, this one is just this. Well, but what is X? X is minus E of Xi, but minus E of E. Yes. So what we see, where X is minus E of E. So what we see that this property is true for linear bundles, and for linear bundles it's just definition of our first Chern class. So our definition is organized so that for linear bundles we immediately just see that the first Chern class is just nothing but a Euler class. And keeping this in mind, let us consider. Now let us try to prove Cartan's formula. The proof of Cartan's formula is based on one easy but very, very important observation. This is a very general observation, but it is useful in many situations in topology. Observation is like that. Observation is like that. Assume that you have a manifold which is a union of two open subsets. Let me just consider a manifold which is a union of two open subsets. And assume that we have two cohomology classes. Doesn't matter of each dimension. There are cohomology classes of M. And assume that we know the following. We know that if we restrict the class A to U, then we get 0. And also we know that if we restrict the class B to V, then we always get 0. The conclusion is that if we are in this situation, then if we take the product of A and B, then it's just 0. The product has cohomology classes of M. So if we have two cohomology classes, one of them is 0 on U, the other one is 0 on V. Then the product is 0 everywhere. This is a good exercise. I don't want to prove it in details now. Actually, I'm sorry. Today I didn't have enough time to print a list of problems for today's seminar, but I have this list of problems at least in mind, and I will write them down. And this is one of them. To prove this accurately, what is the matter? The first, why it is true and why it is more or less trivial. Look, if we represent the cohomology class of A by a form which is 0 on U, well, and represent the class B by a closed form which is 0 on V, then of course the product of two forms will be 0 everywhere. The matter is that it is not completely true that if the restriction of it as a cohomology class is 0, then we can represent it by a form which is 0 everywhere we should be careful about this. There are some problems with compactness. Just one example. If we take say a circle and take standard from phi, it is non-zero. It has non-zero homology class. It integrates to pi. Yes. If we take for u the complement of a point, then of course the homology class is 0. But of course we cannot represent phi by a form which is 0 everywhere except for this form. We can do it 0 everywhere except of a neighborhood of this point, but not everywhere except for this point. So we have some difficulties here, but this is a good exercise. But this is definitely true. And now I will use this simple fact. How to use it? Let us consider the following situation. I need to destroy this one. Well, how the so we have two line bundle, two bundles, E1 and E2 are two vector bundles of some dimensions Cn1 and Cn2 of M, and I would like to consider their projectivizations. So I have a projectivization of the direct sum, I have the projectivization of E1, and I have got a projectivization of E2. Of course, here we have projections, yes, and here we have inclusions. Well, this projectivization is just all lines over a point here. We have all lines in the fiber of direct sum. But here we have all lines in the fiber of the first sum, and here we have all lines which lies in the second sum. So we have the same for direct sum. We have inclusions here, and we obviously have the same for projectivization. So let us think of these two projectivizations as of subsets of this P. And what I would like to say, that of course this PE of PE1 and PE2 are closed subsets of the whole projectivization, but proposition is that these two subsets are deformation retracts of the complements of each other. So PE1 and PE2 are deformation retracts of the complements of each other in the projectivization of the sum. Why? This is just a standard exercise in linear algebra. If you have got a direct sum of two vector spaces, so this is E1, this is E2. This is a picture in one fiber. This is a picture in a fiber. If you have got a line which does not, this E1 and E2 are not one-dimensional. We have several dimensions here and several dimensions. If we have got a line which is not in E1, then we can move it continuously so that it gets to E2. We just can project it, and we can project it not in ones, but we can continuously projected so that it gets in E2. And if we introduce here some Hermitian metric, then of course we can just do it canonically. We can write down this projection just by an explicit formula, how we project it. And if it is not in E2, then we can project it to E1. And these are exactly those deformation attractions. So all lines which are not in E1 can be moved to get into E2. All lines which are not in E2 are moved so that to get into E1. And we take, now I would like to get into this situation. So I would like to, for manifold, I take this projectivization of direct sum, and it is the union of U and V, where U is the complement of projectivization of E2, and V is the complement of the projectivization of E1. And of course they together they give this, they are open, and that's all. Now let us consider here this tautological bundle C. And of course its restriction to here and to here is those tautological, the corresponding tautological bundles C1 and C2. Well, we can restrict and get tautological bundles here. What can we say? Yes, and as usual we put X is minus Euler class of C, and it lives in the direct sum. Look, here we have this F, F1 and F2, and if I would like to multiply the ecohomology class in the base to a ecohomology class in some of these spaces, then I should take pullback along F, F1 and F2. I don't want to write this down in the formulas, so I just will write multiplication. I will consider these homologies as modules over homology of M, and I will write formulas without these F stars. Otherwise, they will be too cumbersome. What can we say? By definition, what can we say about Euler classes of the sum? By definitions, they are defined in the following way. First of all, well, dimension of E1 is N1, dimension of E2 is N2, so the dimension of the sum, the rank of the sum is N1 plus N2. So we have such formula. This is the definition of Cherry classes of this bundle. But let us also write down the definitions of Cherry classes of this and that bundle. To do this, let us denote. I would like to use here letters x1 and x2. These are minus Euler class of those tautological bundles. x1 lives here and x2 lives here. So we have we have this definition of shared classes of the bundle E1, and we have the same definition of shared classes, C1 here, of E2. Yes? Now I would like to do the following. Oh, here we have x1 and here we have x2. Let us consider the same expression, but I would like to replace x1 with x. So now the left hand side here is the cohomology class in P1. But I would like to write down the corresponding expression, and this will be A. A will be the following. X to the power n1 plus c1 of e1. X to the power n1, n-1 plus and so on cn1 of e1. Where does it live? It lives in the cohomology of this projectivization. I always mean here that to be honest, we need to write f star of these shared classes everywhere, but I said that I don't want to do this. Well, so we live in cohomology here. This is not zero. I don't claim that it is zero. I just write down the same expression. But what we know, and I would like to write down similar expression for n2. Again, this is a class in the homology of this projectivization. But what I want to say, I would like to say that if I restrict A to P of E1, then I get 0. A itself is not 0. But if I restrict this A to here, then X restricts to X1, and I get 0. So I know that A restricted to P of E1 is 0. Well, and similarly, and now this observation, P of E1 is a deformationary tract of this U. So the inclusion of P of E1 to this U is a homotopy equivalence. So if A restricted to P of E1 is 0, then A restricted to U is also 0. The homotopy equivalent, their homology are isomorphic. So similarly, B restricted to P of E2 is 0, and hence B restricted to V is 0. So look, we are exactly in the situation of those observations. We have two cohomology classes, this one and this one. Themselves, they are not zeros, but we know that one of them becomes 0 when we restrict to U, and the other becomes 0 when we restrict to V. Hence, their product is 0. And let us, I erase here, and I know that their products, AB, which is just this is just 0. Well, but if we open brackets and take summoned with the same power of x, then we get exactly, so we have this relation and we have that relation. But we know that we have only one relation of this type. There is only one way to express x to the power n1 plus n2 from x's in smaller powers. There is only one way to do this. So we have that coefficients in this expression are equal to the coefficients in that expression. Just we cannot have two relations of such type. By the Rayhirsch theorem, x's from 1 to x to the power n1 plus n2 plus minus 1, they are free bases of H star of M model. So we see that coefficients here are equal to coefficients there, and we exactly arrive to this formula, to this Cartan's formula. Well, so we have this formula. It is a really powerful tool to compute shared classes of bundles. Very often we are able to decompose a bundle into direct sum, and then we can write down.
A question.
Yeah.
So how to say that x restrict to x1 when from the
Look, we have here the topological bundle. It restricts here to the topological bundle.
yes.
X is minus Euler class this bundle, and x1 is minus Euler class of that bundle. And Euler class has this naturality property. We have proved it. So it's just naturality property for Euler class.
Yes.
Well, now, actually, yes, we proved this Cartan's formula. But now, what can we say? From this, we can immediately obtain that we have stability. Indeed, one more trivial case. What happens if we consider a trivial vector bundle? What happens with our construction? Of shared classes. Well, if our bundle is just trivial, it's just direct product, what happens? Then differentialization is also trivial. It is also a direct product. And what can we say here? When we write down here, of course, we have this plus x, which comes from the standard generator U here, yes. And by Kuhn theorem, we have, in the case of direct product, we have not only isomorphism of modules, but we have isomorphism of algebras. Yes? For Kuhn theorem, we have this generally. This is just isomorphism of algebras. Yes? And here we have exactly this situation. So we just see that, well, this is P of E in our situation, yes? And H star of P of E is just isomorphism of algebras. H star of M, tensor, this multiplicative isomorphism. Tensor, the homology ring of this. So we just arrive at equation x to the power n is 0. It is 0 in once we have a multiplicative isomorphism, then of course it is 0, and hence all shared classes, this is not surprising, and it is very natural that all shared classes of trivial bundle must be trivial. And indeed, our construction yields this, that all shared classes, except for C0, which is always 0, yes, which is always 1. All shared classes of trivial bundle are trivial. And then stability follows exactly immediately from this formula. The only, if E2 is trivial, then the only non-zero summed is C0 of E2, and we get just that shared classes of E1 plus E2 are equal to shared classes to the corresponding shared classes of E1. So we get stability from here. Well, so what we see, we see that yes, we have proved stability, we have proved Cartan's formula. The only thing which we have not proved is that the Euler class, the highest shared class, coincides with the Euler class. We have proved this only for linear bundles, only for one-dimensional bundles. But in general situation, not. But to prove this, actually there is another very important point of view on shared classes, and let us discuss this. This point of view is called the splitting principle. What is this about? Well, it's very nice. We would like to work with of rank n vector bundles. It is very nice to work with those bundles which split into direct sum of linear bundles. It is harder to work with those which do not split. So the idea is to split any bundle. We cannot do it immediately, but the idea is the following. So now it's a theorem. Theorem says the following. Consider an arbitrary n-dimensional bundle. We would like to split it. We cannot split it just here, but we would like to do the following. We would like to find another manifold and a map here so that the pullback splits into the sum of linear bundles. It is not so interesting if we do not have any additional information. The matter I can take point, map it to here, and of course over a point any bundle splits. It's not interesting. But the idea is to do this without losing information on cohomology. So our requirement is the following. So first of all, we would like that this splits into direct sum of linear bundles. So theorem is that for any bundle E, there exists this manifold M prime and map from E to M with the following property. So first, the pullback splits into linear sums, where Ci are linear. Linear means one-dimensional. And second, we do not lose anything in cohomology. So if we take pullback in cohomology, then this is an injection. So we have some cohomology here, and here we do not lose anything of them. So the requirement is that F star from H star of M to H star of M prime is injection. this theorem is called splitting principle. Let us understand that we almost proved this theorem. we all
Or we can take the project.
yes. We can take the projectivization of this bundle E. Yes, and what we know, we first we do not know that F star splits, but we know that this F star contains a linear subbundle. Yes? But what does it mean? We can, for each bundle, we can always introduce a Hermitian metric in it. So if we have a linear subbundle, then we always can consider its orthogonal complement. So look, it is not complete splitted, but at least we have one linear summand here.
Then we.
Yeah, then we can iterate. But also, what we know that H star of P of E, yes, is a free module, is a free H star of M module. We have discussed this many times during today, with basis 1x, so 1x and minus 1. It is important for me that we have 1 here. This means that just if we pull back from here to here, then we get exactly this. So we have that H star of P of E is H star of M additively plus H star of MX plus etc. But we have this summand, so when we take pull back, we inject onto this summand. So we definitely see that we see this second condition. Well, and then we just need to iterate this. We still have Xi orthogonal complement, which is not splitted yet, but we can iterate, which take the projectivization of it. We have one more summand and so on, until we get this complete splitted. So this is just the proof of this splitting principle. When we have this theorem, then look, we can do the following.
We really say again how to further decompose the bundle to make sure it's n copy of linear.
No, this is not n copies. We have different linear bundles.
Oh,
So I do not insist that.
Yeah, it's not copy element.
Yes. Look, now we take this P of E. We think of it as of M. This one is always linear. Let's forget about it.
Okay.
Let us consider this one, and let us take the projectivization of it. And we have here projectivization of this Xi. And we iterate this construction. But now, if we pull back this, we have one small linear summand.
Okay.
And the complement of it, again, if it is not linear, then we again take the projectivization. But the rank decreases, so we achieve that all summands are. Look. What can we say about it? Now, now having this in mind, let us consider this bundle. What can we say? What is the total, the full Chern class? The total Chern class is correct. English name, I'm sorry. Yes, no, not full total Chern class. I'm sorry, this is just in English. The total Chern class of a linear bundle, what is it? It is just 1 plus first Chern class. We don't have higher Chern classes, yes?
Yeah.
Jenny, total Chern classes by definition 1 plus sum of all Chern classes. But for linear bundle we have only 1 plus first Chern class, which is the same as, I would like to write it in the form, I would like to take here Ci, and I would like to denote this by Xi. Let it be Ti. This is not the same X which was before. Another. Ti is just the Euler class of this Ci. Yes. Or is the same as first Chern class of this Ci. I just would like to introduce this notation. All this lives in cohomology of M prime. Well, what can I say about Chern class of F star of E? Chern class of F star of E, a total Chern class of F star of E, we have this split into linear bundles. So by Cartan formula, we have, which should just multiply all total Chern classes of summons. So we get this very easy formula. 1 plus T1, 1 plus T2, and so on, 1 plus Tn. What we get if we open brackets?
No, it would be sum of elementary.
Yes, it would be sum of elementary symmetric polynomials of T1, Tn. It will be 1 plus first elementary, I denoted by first elementary polynomial is of course just sum of this Ti, plus second elementary polynomial, etc. And the last is the product. And these are exactly homogeneous components. So this is exactly C1 of F star of E. This is exactly C2 of F star of E. And this is exactly Cn of F star of E. But now, once we know that this pullback is an injection, let us identify a cohomology of M with the corresponding subring of cohomology of M star. So identify cohomology of M with F star of cohomology of M. Then I can erase F star here. First of all, I can put F star by naturality, I can put it here. But then if I identify cohomology of M with subring, then I just can erase it. And what we see? We see the following. Look, these Ti, they do not live. We can, an important point is that we can make calculation in M using these very convenient variables Ti. They do not live in the cohomology of M. They live in some larger ring. But their elementary symmetric properties always get in cohomology of M. So we have the cohomology of M are embedded into some larger ring. And these Ti's lives here, but all their symmetric polynomials live in the subring. So we can make computation using these variables Ti, which are not well defined in the cohomology of M. But we get a result which is well defined in the cohomology of M. We get some formulae which are well defined. So these Ti's are called, well, old name is Wu variables, but now it is always called Chern roots. So it's better to use, more common to use this name. They are called Chern roots of our bundle, and it is a very convenient formalism. It is a very convenient formalism. We can work with our bundle as it is splittable. It is not splittable, but we can work with it as if it is splittable. So we work here, and it doesn't matter. We do not need to choose precisely this M prime. We just need to know that it exists. So we just write down formula. This Ti proves some formulas, and then replace elementary symmetric polynomials with shared classes of the bundle. And all formulae are correct because this is an injection, because we do not lose any information. And this is very nice point of view. So this theorem, we can say that this is an alternative definition of shared classes. What is an alternative definition? Just we can split, then we take elementary symmetric polynomial in Euler classes of this C1, Cn, and these are by definition shared classes. And it is a convenient way to work. And well, I'm sorry for delaying with time. A nice thing which we see is that the highest shared class, yes, is just the product of Euler classes of these sums. But we know that we know the same property for Euler class. We know that the Euler class of direct sum is the product of Euler class. We have proved. So this is E of f star of E. And again, since it is an injection, then the same is true for an arbitrary bundle. For splittable bundle, it is directly from this formula, but now, by splitting principle, we have this for arbitrary bundle. I haven't succeeded to say everything I wanted to in the lecture, so during the second part we start again with some lecture part, and the seminar will be shorter. Well, now let's have a break for, say, 10 minutes. Ой, I'm sorry. It's too late. Так, что я должен сделать? Так, вы запомните. Я подпишу. Ну, здесь, понятно. Вот здесь. Вы запомните, я пишу.
Не было какой-то инфы про КР?
Вот хорошо, следующий лекции.
Ну, вообще, интернет.
Ну, следующий, мне кажется, чуть затянется надолго. Потому что
Деловой год.
он скажет, что записки всегда положит сегодня, положит во вторник. Они не выведились. Так что
Ну, нормально, ничего.
можно там не ждать работы. Пока что.
Ну ладно, уж придумать что-нибудь.
Так, вот здесь я должен записаться, да? Спасибо.
Не сложно это вот написать.
В связи с производственной необходимостью. В связи с производственной необходимостью.
Можно написать.
Нет, не надо.
У нас 10 минут? Уже 5, да?
Ну, 5.
Хорошо.
proceed. And actually, what I want to say now is a very nice integrality properties of these Chern classes. In fact, true integrality properties are as follows. True integrality properties says that all this stuff, all what I said, can be said in integral homology, in integral singular homology. So, in fact, all Chern classes are integral homology classes. But what we see on the level of Derang theorem. On the level of Derang theorem, we can see the integrality of integrals. I'm sorry for this problem with words, but these are actually different words. We integrate Chern classes, and the integrals are integers. More directly, we have the following. So, theorem is that assume that we have E which is a bundle over some manifold of even dimension. Suppose that it is arithmetic. Then what can we say? We get here, suppose the manifold there, and compact. Now I want to say, what I want to say is about compact manifolds without boundary, so closed manifolds. Assume that we have such situation. Then what can we do? We can compute Chern classes. Well, we have C1 of E, C2 of E. These are cohomology classes in cohomology of M to K. And then we can consider any monomial in Chern classes which has total degree to K. So each Chern class has degree 2i, where I is the number of this Chern class. So we have degrees 2, 4, and so on. We can multiply this Chern class so that to get a monomial of total degree to K. Well, for instance, general situation is that we can multiply C1 to some power K1, C2 to some power K2. I'm sorry, I don't want to write this E, just, and so on, C, S, K, S, where we have K1 plus 2K2 plus SKS equal K. If we have this, for instance, if M is, say, 8-dimensional, then what can we do? We can consider C1 to the power 4. Well, this is monomial of total degree 8. Or we can take C1 to the power 2, C2. Well, or we can take C1, C3, or we can take C4, or we can take C2 squared. Well, in dimension 8, only 5 variants, but generally, well, we have some number of variants. And then we can, then this is the class of the top dimension. And then we can integrate this class over M to K. And the assertion is that it is always integer. So we have such strange thing that we integrate something, but the result is an integer. Why? In fact, well, I want to say that before proving this, let us discuss it. Well, in fact, these CIs are integer cohomology classes, so it is not surprising that when we multiply them, we again get an integer homology classes, and when we pair off this class with the fundamental class of the manifold, then we get an integer. So on this level, it is more or less clear. Actually, this statement is weaker than the statement of integrality of these Chern classes. Let us explain why. In fact, what does it mean? What is the corollary of this theory? Assume that we have an arbitrary manifold of arbitrary dimension and a vector bundle of it. Then we can consider various manifolds oriented. For M, we even do not need orientability, but we can consider various oriented manifolds and their maps to F, to M. Well, we can take various oriented manifolds and map them to M. And we can integrate not over M, but we can integrate over these images of manifolds. It is very nice when it is a submanifold, and we can just integrate over submanifold or over an immersed manifold. But actually for arbitrary map, we just need to take the pullback and then integrate. So we can integrate over arbitrary maps of such. And of course, what we see that if we would like to integrate over n of some monomial of such kind, well, then of course, now I would like to write here. Then of course this is the same as to integrate over n. We can first take pullbacks of these Chern classes over, and hence by naturality we can take pullback of the whole bundle, and we can put here monomials of pullbacks. And we get 0 by this theorem applied to the manifold n. Well, so what we see? Actually, we see that if we have, this theorem implies that if we have a vector bundle over an arbitrary manifold, then we can take any smooth cycles into it. Smooth cycle, smooth submanifold, or even immersed manifold, or even mapped manifold. And any monomial of Chern classes, and the integral is always the integer. Well, this is just a corollary of this theorem. Not only about the integral over the fundamental class, but the integral over any such smooth cycle in M. This is just corollary since we can take pullback, and this is immediate corollary. But why this is weaker than to say that classes are integers? In fact, if we know that these classes are integer cohomology classes, then we can integrate not only over smooth cycles, but we can integrate over any singular cycle. We can glue of synthesis some cycles with singularities and integrate over them. And the integral will be always an integer, even for singular cycles. And it is strong assertion. And I'm not going to speak about this strong assertion. We will discuss only that integral over smooth manifolds is integer. So I just would like to stress that this is weaker than the assertion which comes from singular homology theory. From singular homology theory, we can deduce more. But to obtain this integrality is always also very important. Actually, well, It is always a nice property if we can say some things about integrals. But to prove this, we just can use, it is enough to have only Dirac homology theorem. Well,
Just a second, I don't understand why these two integrals are equal.
more or less by definition.
But how do you integrate over n for
Integral over n is more or less by definition. This is by definition we have that integral over n of f star of this. How to integrate a form over a cycle obtained by a map? Just pull back and integrate. This is more or less by definition.
okay.
And the second, and this equality is by naturality.
Yes.
So this one is by definition, this one is by naturality.
Okay.
Sorry. Извините, вот если по-русски, ну
Да.
даже, по-моему, вот перед интегралом должна какая-то степень вывести отображение, когда мы от m к n там переходим.
Здесь интеграл тоже по n. Если мы сравнивали интеграл по n и по m, и они были по одной размерности, то да. А здесь ничего не вылазит, это вот просто как иначе определять интеграл по... Ну, если бы это было вложение, то это просто очевидно. А если это не вложение, то это кроме меня определение интеграла. Okay. Well, let us understand why this is true. And the most important thing is that, well, let us start with the first Chern class, which is Euler class. And here, we have the following situation. I just would like to remind that if we have a Euler class, let us consider one particular Euler class. There is one situation when we already know this assertion. Very trivial situation. If we have a tautological vector bundle over CPN, yes, then the first Chern class is the Euler class, yes? This is just not arbitrary but tautological. And we have already understood that if we take yes, what we have already understood. We have said that the Euler class of C is the minus standard generator. The standard generator is obtained for dual to tautological. Well, but for tautological it is minus standard generator. And this standard generator is just the Poincare dual to CPn-1. This is what we have discussed. This is minus the Poincare dual to CPn-1. Hence, if we integrate it by CP1, we get -1. I recall that integration of Poincare dual is that just taking the algebraic intersection index, algebraic intersection number with some manifold, and we can do it. CP1 and CPn-1, we can put them in transverse position and they have one intersection point, so it is just -1, and we see this integrality, yes? So in this particular case, the first Chern class of, but the first question is, well, let us consider this situation. Assume that we have an arbitrary two-dimensional manifold. Oriented two-dimensional manifold is just sphere with handles, just genus G, sphere with handles. And we have an arbitrary map here. Is it true that the integral will be also an integer? Just in this particular case. We know this for the standard sphere in CPN. Let us understand for this particular C, but for an arbitrary manifold. How to do this? The main idea is as follows. General idea, which will help us not only in this situation, but in general situations too. Assume that we have a manifold, and we have a submanifold. All these manifolds, submanifolds, and so on are compact without boundary oriented. Everything is compact without boundary and oriented. Assume that we are in such situation. Then we have the Poincare dual of this manifold, which lives in, this is dimension S, this, which lives in the homology of N. Well, we have constructed this. Assume that we have got a map from some another manifold N to M. Again, everything is oriented. We can put this map into a transverse position with S. This is Thom's transversality theorem. I said that I don't want to prove it in full generality, of course, but I will use it. It is rather technical. What does I can put this map F by an isotopy in transverse position to S? What does it mean? This means that at every point P, which if we are if its image is in S, if f of P belongs to S, then we can take the sum of tangent space N and tangent space to S. And this must be the whole space of N. So we always can achieve by an isotopy that this transversality condition is fulfilled. If it is fulfilled, then we get here a full preimage of S. Well, a very nice exercise, which should also be in the list for today's seminar. I'm sorry. It seems that the list will be on time, that when we finish the lecture and the time is over, and then I send the list today in the evening. So I'm sorry for that, but still. Exercise that first of all this full preimage is a smooth submanifold, and second is a smooth submanifold of N, and we can say it is of the same codimension as S. So its dimension Well, more or less, S is given locally by some equations here in M, and we have the same number of equations, and they are also independent locally. Well, so we have the same number of equations, so codimension is the same. This means the dimension is S plus N minus M. The same codimension is exactly this. And second, very important, is that we can say something about normal bundles. Look, you have normal bundle of S in M here. Once we have a submanifold, we have a normal bundle. And we have normal bundle here. And I claim that it is exactly the pullback of those normal bundles. So second is that normal bundle of this pre-image in N is the pullback along F of normal bundle of S in M. So this is a good exercise. In fact, more or less, it is more or less straightforward from this requirement, this reciprocity requirement, just.
We require this.
Yeah. Yes, it's. I'm sorry. I mean exactly this, that if transversality condition is fulfilled, then this is true. In general, of course, if you take an aperture smooth map, then a pre-image can be very nasty. It mustn't be. It cannot be a submanifold. Maybe a submanifold, but maybe not. But if we have transversality condition, then we always are in this very good situation. What is the consequence? Look, we had here for this S, we had a tubular neighborhood. Yes, I would like to write it down like that. Look, this S, it has a tubular neighborhood. This is a picture in M. Yes? And here lives the Thom class of this bundle. It lives here. It is just, we can consider particular form. It is form which is 0 outside, and it is something like that. And it integrates to 1 over every fiber of this normal bundle. When we have F here, and here we have the same situation. We have N, and here we have some F, the pre-image of F, yes? And here we have tubular neighborhood. And in fact, this transversality condition implies, I explain why this is true. If we have a point P here and a point F of P here, then transversality condition says that this fiber goes isomorphically on the fiber here. What does it mean? It means that if I take F star of phi, then I get a well-defined Thom form here. So Thom class here comes from Thom class there. But it immediately implies that Euler class, actually from here, we say that any characteristic class of this comes from characteristic class of this. By naturality, Euler class, and so on. But another important thing is that this Thom class is related. I would like to remind you that if we take this Thom class and extend by 0 to the whole manifold, then we get the Poincaré dual class to the submanifold. Well, so this Thom class extended here is the Poincaré dual of submanifold. and this top class extended here is the Poincare dual of this complete pre-image. Well, so we get this assertion. I would like to say that this is a proposition. Again, if we have this transversality condition, so if we have this transversality, then the Poincare dual of the complete pre-image of F in N is the pullback of the Poincare dual of S in M. Well, why this is nice? Actually, look, not all de Rham cohomology classes are Poincare duals of manifolds. There are. So if we have a submanifold, then we have Poincare dual of it. But it is not true that any cohomology class comes as a Poincare dual of a submanifold. But among all cohomology classes, we have those which are Poincare dual of submanifolds. Poincare duals of submanifolds. Well, and look, what does this proposition says? That if in M we have a cohomology class which is Poincare dual of some submanifold, assume that we know that X is a Poincare dual of submanifold, and we have an arbitrary map from M to M. So if S is a Poincare dual of a submanifold then its pullback also satisfies this condition, is also a Poincare dual of submanifold. Why? We take this submanifold, we take arbitrary map, then we can isotope this map so that to obtain that it is transverse to S. Well, and then we just take the full pre-image and we know this assertion. So we see that among all cohomology classes, we have those cohomology classes which are Poincare duals of submanifolds. And this set of cohomology classes is closed under pullbacks. This is an important observation. Well, why? And also, I would like to recall that we had proved the following nice. Assertion that if we have two submanifolds in M, then the Poincare dual, and we can always put them in transverse position by isotopy of one of them, and the Poincare dual of their intersection is the product of the Poincare duals. So look, among all cohomology classes, we have this set of Poincare duals of submanifolds. We know that these classes are closed under pullbacks and under multiplication. These two operations do not lead us out of this class. If we have some cohomology classes which are Poincare duals of some submanifolds, then, and we start take pullbacks of them and multiply them. Then we are still in this class. Well, so pullbacks and multiplication do not lead out of this class. Now look, we know that at least up to sign, well, to be honest, the minus the Euler class of tautological bundle over CPN is the inside this class is a Poincare dual of a submanifold. Yes? Yes, it's up to sign, it's the Poincare dual of CPN minus 1. But now let us look on our general construction of Chern classes. And I prefer those constructions which deals with splitting principle. What do we do? First, I would like to define Euler class of. I want to say that all Chern classes are in this class. Well, first we see that all Euler classes of line bundles are in this class, since they are pullbacks of this particular one. And then what we see? We see that using splitting principle, we can think of the Chern class of an arbitrary bundle. We can reduce the problem to the split bundle. And then we see that we should multiply the classes in this set. And we always are here. Actually, it is, I'm not completely honest here. To be, I don't want to, in fact, it is true that Chern classes are always Poincare dual of submanifolds, but I don't want to it is easier to prove somewhat weaker statement. Actually, it is not so easy that this set is closed under addition. It is closed under pullbacks and under multiplication. But if we would like to prove that it is closed under addition, we need some further difficulties. The matter is that if you would like to add two classes which are Poincare duals to two submanifolds, then these submanifolds may intersect. We would like to have the disjoint union of this submanifold, but they may intersect, and it is not so easy to. So I can just extend this set. I just
linear span.
I prefer to say sums of Poincare duals to submanifolds. Then it is closed under pullbacks, addition, and multiplication. However, in fact, it is not necessary. And then any polynomial with integer coefficients of Chern roots is again in this class. So we see that Chern classes are also here. Chern classes of arbitrary bundle are here. Just we see that starting, all of them are obtained by our operations pullbacks, multiplication and addition, starting from Euler class of this particular bundle. It is in the class, hence all of them are also in the class. And now let us see what does it mean. Well, what does it mean? Now,
I think that about classes we can quickly say that it is something like integer lattice obtained.
yes. This is exactly. This is something like.
Suppose we have minus and
Yes. These are integer lattice, and we know that all our Chern classes are inside this lattice. And now, what do we see? Assume that we are in the situation of the theorem which we are trying to prove. I am sorry, I have already erased it. So we have bundle over M. We have such decomposition of K, and we have the class of total dimension. Yes? Sorry, C1 to the power of K1, Cs to the power of K plus. Well, like that. It is the total. So we know that this one is some
intersection numbers.
is linear combination instead of sum, it's better to say linear combination with integer coefficients of Poincare duals of submanifolds. We know that this is in the class of Poincare duals of submanifolds. But it has maximal dimension. What does it mean? These submanifolds are zero dimensional.
Points.
These are points. We have no other submanifolds of dimension zeros. So it is our class is linear combination with integer coefficients of Poincare dual of points. But what is a Poincare dual of points? This is a form which integrates to 1. A form in the neighborhood of this point which integrates to 1 by definition.
Bound functions in both.
Just some height form. Yeah. So it integrates to an integer number. It is just a combination of these forms, each of which integrates to 1. So it's after we understand that our Chern classes are in this class, it is just straightforward that they integrate to integers. Their integrals are zero. Integers, so not zero. Well, that's the claim. Well, and actually, this is important integrality properties, just maybe I would like to say something in advance that this integrality of characteristic classes has very far consequences. For instance, it lies in the maybe you heard about Milnor's result on non-standard smooth structures on S7 on sphere. There are non-standard smooth structures on spheres, and at least on S7 they are immediately distinguished by some non-integrality properties. The proof that a smooth structure is non-standard sits on the fact that if it were standard, then we would obtain some non-integrality. So it sits on some non-integral, on these integrality properties, and a lot of things in topology sits on these integrality properties, so they are very important. And the second thing which I would like to say is that all this stuff concerning shared classes has a very nice real counterpart. Up to now we always speak about complex vector bundles. Let us now speak about real vector bundles. Actually, there are two versions of this stuff of this theory for real vector bundles. One of them is called Stiefel-Whitney classes. These well, it is more or less natural that in complex situation we have characteristic classes in every second dimension, in even dimensions. But here we have characteristic classes in every dimension, but with coefficients in z over to z, and this is why we cannot see this on the language of Dirac cohomology at all. So we cannot say anything about Stiefel-Whitney classes on the level of Dirac cohomology. We have no good theory for Z2 cohomology. But another theory is with Pantragen classes. Which surprisingly live in 4i, in dimension 4i, with coefficients in z. And again, I would like to say on the RAM version of this theory, how to obtain Pantragen classes have images in cohomology with the real coefficients, so we have this Dirac version. Well, and I would like to say about Pantragen classes. I will not say anything about Stiefel-Whitney classes. And about Pantragen classes in Dirac cohomology, so we forget about torsion. We come to and forget about integral structure. But finally, we obtain the same integrality properties. Well, what is this about? The most why we cannot make completely the same theory for real bundles as for complex. We can try to do completely the same. We have a real bundle, and what we can try to do? We can try to take the projectivization. Yes. But what is the cohomology of Rpn minus 1? It is a good exercise to compute the cohomology of Rpn minus 1, but they are almost trivial. We dependent on we have zeroth cohomology, and we have maximal cohomology when Rpn minus 1 is oriented.
Taking the two thing.
Yes, and that's why Rpn projectivization is not good thing. We do not have this polynomial structure in something like Euler class. We do not have any another. So instead of projectilization, a good idea is to take Grassmannization. What is a projectilization? We take one-dimensional, what is a projective plane? We take one-dimensional subspaces, but we can take two-dimensional subspaces instead of one-dimensional, and it turns out that then it works. So instead of incomplete situation, we had CPN as the base for our theory. CPN is good. RPN is bad for this, so it behaves badly. It behaves nicely over Z2, and Stiefel-Whitney theory sits here. Over Z2, RPN minus 1 is nice. It has exactly truncated polynomial ring. It's a cohomology. But over Z or over in the round setting, this is bad object. And good object is Grassmannian of let it be like that. Real Grassmannian, I will not write R always, but real Grassmannian of two-dimensional planes in Rn. So this is Grassmannian. So a point here is of two-dimensional subspaces of Rn. It is a standard and good exercise to prove that this is a smooth manifold. But okay, but and first, what we want to start with. In this situation, we started with understanding what is the cohomology of CPN. Well, so it is natural to start with understanding what is at least the round cohomology. Now I want to say only on the round cohomology. What is the round cohomology of this Grassmannian? And well, in over CPN, we had what was situation over CPN? Over CPN, we had a tautological bundle. We took its Euler class, and the cohomology were generated by powers of this Euler class. Can we take Euler class here? Of course, over Gn2, we again have Gn2. We have this tautological two-dimensional bundle. Well, can we take the Euler class of it? The answer is not, because this bundle is not oriented. Look, if you have a two-dimensional plane in Rn, where n is sufficiently, or even in R3, I can do like that. I can reverse the orientation. Yes? So this bundle is definitely not oriented. So we cannot take a Euler class of it. But what can we do? We can do the following. Let us consider the Grassmannian of oriented planes. A point here is a two-dimensional subspace of Rn. A point here is an oriented two-dimensional subspace. So it is just a two-fold covering. We forget about orientation. So to each subspace here, we have two oriented subspaces with two different orientations. So this is just two-fold covering of a very nice object. Two-fold. And here, of course, if this is, well, let it be P. No. Let it be P, yes. Then, of course, this bundle is oriented, yes? So, for incomplete situation, I was very precise and I go in all detail. Here, I suggest that I give a series of statements which are just tasks for you. Here, the situation is very similar, but I don't want to. So this is a problem. problem for you. And first, what is the cohomology of this guy? What is the dimension of the Grassmannian?
2 on n minus 2.
No, 2 on n minus 4. Look, we need to choose 2 orthogonal unit vectors. How many ways to choose in Rn? Yes? How many ways to choose the first vector?
We use only
N minus 1.
orthogonal.
It doesn't matter. If we use not orthogonal, then we need to take quotient and still we will get the same number. If we use orthogonal, then n minus 1 dimension for the first vector.
Minus n.
Plus, because it is unit. This is sphere. First vector is on the sphere of the dimension n minus 1. We have n minus 1 dimensions for the first vector. The second vector must be orthogonal to the first one. We have n minus 2 dimensions for that. And also we should take minus 1 because we have one parametric sets of bases in each subspace. Now when we get a subspace, so on the set of these bases, a circle acts by rotations, and we should take quotient by this circle. So we have minus 1. So this is also a good exercise that this is a smooth manifold of dimension 2n minus 4. And this
Yeah.
2n minus 4. Yeah.
I mean that it can, usually it writes like k multiplied on n minus k.
Yeah. Exactly. So first, we can say what is de Rham cohomology ring of this oriented Grassmannian. And claim is that the de Rham cohomology ring of oriented Grassmannian is the truncated polynomial ring. U will be the Euler class of this bundle. Now it is oriented, so we can take the Euler class of this bundle. So it lives in 2-dimensional cohomology. And here we have the quotient by the, if we take to the power n minus 2, it is still non-zero, it is top dimensional, and to the power n minus 1, it is 0. So this is first assertion. That we have the following. This is completely similar to the case of Cyprian. Well, second, we have this map P, and it is natural to describe. We are interested not in this cohomology ring, but in that cohomology ring. We are interested in non-oriented Grassmannian. And for that cohomology ring, the result is as follows. First of all, this P star, this pullback along P, is an injection. And second, it is an injection on the subring here generated by the square of U. So this is exactly the second exercise, that P star from cohomology ring of non-oriented Grassmannian to the cohomology ring of oriented Grassmannian is an injection onto the subring generated by U squared. So, in a sense, for non-oriented vector bundle, we do not have the Euler class, but we still do have the square of the Euler class. For those who know about cohomology with local coefficients, I just say that in fact Euler class here exists, but it is not with direct coefficients, but with twisted coefficients. But when we square it, then we get into usual homology. But we cannot think about this, but we can just prove this assertion. And so what we see, that the homology ring of this GM2 is the truncated polynomial ring with generated in degree 4. So let us denote this generated by V. Here is, we need to put V to the power k, where k is the upper integral part of n minus 2 over n minus 1 over 2. So, and this V, P star of V is the U squared. So if I identify this subring, this ring with its image here, then V is just U squared. So in non-orientable case, we do not have U, but we have this generator V. And now we can do the whole, we can repeat the whole construction in complex case. We can repeat it in real case using this V instead of the two-dimensional generator U here. First of all, as in real case, as in complex case, we start with, in complex case first we defined Euler class of linear bundles. Yes? And here we also can define, but now it is called first Pontryagin class of linear bundles. Look, if we have a linear bundle, or not of linear bundle, but of two-dimensional vector bundle. If we have a two-dimensional vector bundles, then it always can be, it is again a standard thing that any bundle can be, suppose that M is compact for simplicity, any bundle can be a sub-bundle of a, can be obtained as a sub-bundle of some trivial bundle. And then, this is what we discussed in the beginning, any bundle is a pullback of tautological bundle along some map. Yes? For some sufficiently large area. And once we have this V here, then we say that by definition the first Pontryagin class of E is the pullback of this V. This is completely in agreement with complex situation. In complex situation, we had first Chern class for linear bundle is the pullback. Up to sign in complex situation it was minus 1, here it is not. Up to sign it is the yes, we have two-dimensional class here, and the first Chern class was the pullback of this two-dimensional class in CPM. Here we have like things like that. And now we can completely repeat the construction. Assume that we have an arbitrary bundle of some dimension n, of rank n, over n manifold m. Then we can take, this is pi, then we can take Grassmannization. Instead of projectivization, we take Grassmannization of two dimensions. So this is an associated bundle with fiber Grassmannian of two-dimensional planes in M. Well, so in complex situation we took projectivization, and point here was a line in the fiber here. But now a point here is a two-dimensional subspace of a fiber. As in complex case, we have f star of E here. And as in complex case, we have here a tautological bundle, well, which is, in complex case it was linear, but now it is two-dimensional. Yes? Tautological bundle. And we know that the restriction of it to any fiber is that tautological bundle. Yes? And its first contracting class generates the cohomology ring of the fiber is truncated polynomial ring in this first contracting class. So now we would like to take, it was X in complex situation, now I use letter Y to distinguish. We take the first contracting class of this tautological vector bundle, and it lives in four-dimensional cohomology of this Grassmannization. Well, and what can we say? We can say that if we take 1, y squared, and so on, to the power up this n minus 1 over 2 upper integral part minus 1. It is not a very nice number, but still. If we take these classes, then they form an additive basis of the fiber. If we restrict them to the fiber, then they form additive basis in cohomology. And we can again apply Le-Reicher's theorem. Le-Reicher's theorem says us exactly as in complex case. So Le-Reicher says us that H star of this Grassmannization is free H star of M module with basis 1, y, and so up to this let it be k, this k minus 1. So I would like to put k equal to this to this integral part. I don't want to write down it every time. So it is a free module, and again we can write yk as linear combination of these smaller powers with some coefficients in h star of n, and these coefficients are called contrarian numbers. But now the standard convention is to use this. Now the standard convention is to write it as yk minus. Here is a minus. So this is the definition of contrarian classes. Well, and they exist and unique. And now I would like to say again, it was 1, 2, and the third exercise is to prove all properties of them which are completely similar to properties of Chern classes. But there are some differences. These differences are related to the fact that here it is something about half of n, but not the n. Yes? So we have the following properties of constraining classes. So first, they live in 4-dimensional, by construction they live in 4-dimensional cohomology of the base, and they are stable characteristic classes as Chern classes. But now of real bundles, stable characteristic classes. Second, well, in Chern situation, in complex situation, we had that these classes exist up to dimension 2i, where up to dimension 2k, where k is the rank of the bundle. Yes. Here the situation is as follows. We can say that pi of e definitely equals 0 if I is greater than 2 times rank of e. Oh, sorry. If like that. Well, look, this is not. The matter is that the dimension, the degree of pi is 4i. So these classes exist up to degree which is approximately 2 times rank of e. Not up to degree rank of e, but up to degree 2 times rank of e. So if you have an 8-dimensional vector bundle, then constraining classes exist up to dimension 16, up to 4th constraining class. And if 2i equals to rank e and e is oriented, in complex case we saw that the top Chern class is the Euler class. Here the top constraining class is the square of the Euler class. Then pi of e equals e of e squared. Well, the third, the same Cartan's formula. Pk of e equals to sum I plus j equals k of e plus f, pi of e, pj of f. And actually, the same integrality property and again the same proof, integrality property, says that if we take integral of some monomial, of course of corresponding dimension, then it is always integer. And again the same proof. Everything is proven the same way. And the same splitting principle. Splitting principle but now we need to be somewhat delicate situation is that, of course, we cannot split arbitrary real bundle into sum of two-dimensional ones. The matter is that there exist odd-dimensional bundles, and of course they cannot be assigned a two-dimensional one, but we always can, one by one, we can take two-dimensional bundles, but maybe at this very end there will be a one-dimensional sum. So, splitting principle is like that, that if we take arbitrary real dimensional bundle, then there exists a map like that, such that here f star of E splits into, here we have integral part of n over 2, and all these xi's are two-dimensional vector bundle, so the rank 2 vector bundles, and maybe, I put it in brackets, maybe one-dimensional zeta, if this was odd dimensional. And again, we have for one-dimensional bundle. Look, from this property, for one-dimensional bundle, all Pentragon classes are trivial. Nothing interesting. One-dimensional bundle is just it can be trivial or it can be not trivial, but Pentragon classes do not see this. So the interesting part is only these two-dimensional classes. And again, we can consider their Pentragon classes, and Pentragon classes of E are again elementary. Elementary symmetric polynomials in the first Pentragon classes of these XIs. Yes, and again, f star is injection. And the proof is again in the same way by taking consecutive Grassmannizations. So everything is like that, and also the last property which is nice to prove is that how can we relate Pentragon classes to Chern classes. If we would like to compute the kth Pentragon class of a vector bundle, then we can do like that. E is a real vector bundle. For each real vector bundle, we can consider its complexification. Just take E tensor C complexification, and then we can compute the kth Chern class. And up to sign minus 1 to the k, it is the Pentragon class. And the last, and what happens if we take odd dimensional class here? Odd Chern class here. Then it is always 0. Well, and the last thing, it's time to finish. The last thing I want to say that all this is true in integral cohomology, but we always should say that all things are true up to 2 torsion. In integrals, this formula is not true directly.
We need to multiply on 2.
Yes, it is true up to 2 torsion. So the difference is element of order 2. This one is not true in integral cohomology. It is an element of order 2, and so on. So everything here is in integral cohomology. Everything is true modular elements of order 2, but not directly. Well, so this is the general picture, and well, I'm sorry we have no time. Maybe not today, but I hope tomorrow I will send you some list of exercises, including these ones and also some others, and maybe on the next seminar we discuss them. Well, that's all for today.
Используешь все это заказать.
Можно. Но важно, что их так можно включить.
Важно, что именно как бы
Ну, полезно
без-
понимать, да, ну, что в принципе параллельные теории. Можно их так определить, да, можно их просто так определить и не мучиться этими версионизациями. Но вообще говоря, полезно понимать, что это просто параллельные теории.
Вы в чат,
Да, конечно.
Вопрос я соответствую.
Ага.
Нам сказали, то, что есть дуальность,
Да.
и то, что там, когда дело касается контактов, то в одну сторону да, есть, что можно, ну, типа спаривание на какое-то симметричное, а дуальность только в одну сторону.
Да.
Вот, я хотел спросить, еще не совсем понял объяснение, почему такой теории не существует, и, ну, я не знаю, есть какой-то пример.
Да, сейчас.
Все.
Ну, например, очень простой. Вот, например, тут прямо. Давайте посмотрим. Вот. Сейчас. Нет. Извините. Не так. Не говорю. Значит, вот, например, даже ноль. Вот, например, давайте возьмем, если m целые числа. Что тогда будет получено? Да? Что мы можем сказать про гомологии? Ну, во-первых, гомологии только нульмеры, ничего больше нет, да? Что мы можем сказать про гомологии без ограничений носителей? Нульмеры. Ну, это просто, нет, это просто функции на правда? Просто у нас не дифференциалов нет, просто ноль формы, то есть функции на z. Да? Абсолютно без каких-либо не было ограничений. Значит, это все функции из z в r. Да? А теперь что такое h0 с компактной z? Но это все финитные функции, которые 0 везде, кроме конечного числа. Ну, компактно.
Нет, это понятно, просто, то есть,
все финитные функции, ну, то есть только такие функции, их меньше. Да? Все финитные функции из z в r. Теперь у нас есть спаривание. Линейное. Ну, каким образом? Если у нас есть функция f здесь, да, и функция g здесь, то я могу их спарить и отправить в сумму по целым числам f от g. Правда? И так как вот это вот конечное, то у меня корректно именно будет, да? Ну, а так вот гранитное, то я могу это написать, потому что две произвольные функции я не мог ставить. Вот, а здесь еще отличное, это вещественное число. Вот, теперь смотрите, если мы интересуемся, какие у нас есть, вот если мы интересуемся вот двойственным пространством вот это, то это ровно все функции. Любой функционал инфинитной функции можно поставить таким образом. Хороший упражнение.
сейчас, это не совсем.
Ну, смотрите, как у нас вообще, вот допустим, у вас есть векторное пространство, да? В нем есть базис. неважно, конечный, бесконечный, но базис в смысле, что любой вектор представляется в виде конечной линейной комбинации этих е. Тогда как выглядит произвольный линейный функционал? Ну, каждому базисному элементу предписываем произвольное значение, а дальше по линейности продолжаем. Ну, как вообще линейные функции?
Если так,
Ну, каждому базисному элементу приписываем любое значение, а дальше продолжаем по линейности.
Это двойственный базис.
Да, это двойственный базис. Нет, это не базис, не получается базис. Это двойственный базис в конечном мерном случае.
Ну да.
А что мы видим в бесконечном мерном случае? Смотрите, вот здесь можно написать какой базис?
здесь можно.
Это функция. Функция, которая единична в одной точке,
Сейчас я. А в другой не можно, потому что
а
бесконечно.
в другой мы не можем написать базис. И он на самом деле гораздо более огромный. И вот смотрите, вот здесь базис счетный, а здесь базис несчетный. Несчетное мерное пространство. И если мы возьмем двойственное к нему, то там будет произвольные функции на несчетном множестве. Это будет уже следующий континуумный кардинал, который больше континуума. И двойственное вот к этому будет иметь базис из больше, чем континуумного элемента. Оно никак не может быть счетным мерным. И здесь полно этих самых, как они называются, полно линейных функционалов, которые не приходят отсюда. Ну, другое дело, что их явно построить практически невозможно, потому что это все с такими логическими сложностями сталкивается.
Да.
В принципе, их здесь полно-полно. То есть вот для этого двойственное это вот это, двойственное к этому, это не это надо написать здесь базис. Ну, вот, основная проблема именно в том, что если вы берете базис в пространстве, бесконечно мерный, и берете двойственные дельта функции в s звездочке, то они не порождают все в s звездочке.
Сейчас.
В s звездочке больше, чем конечные комбинации.
Почему это сейчас порождается?
В смысле?
Почему? Когда мы берем линейный функционал компактно,
Когда мы берем линейный функционал в компактно, то мы приписываем каждому гибитому значение g от n произвольное, да? И вот это g от n могут быть совершенно любым, то есть мы как раз получаем все возможные функции на z. Ну, вот как раз у меня есть дельта, у меня базис вот здесь образует дельта функции, дельта n это дельта функция f, которая единичка в n. И я могу сказать, что дельта n я могу отправить совершенно куда угодно. Давайте мы это обозначим g от n. И тогда вот функция g ровно задает мне именно этот функционал. Но в обратную сторону я не могу этого сделать. Потому что дельта функции не образует базис. Здесь базис гораздо менее приятный. И двойственное пространство будет гораздо больше. Ну вот мы уже здесь видим. Было счетное мерное, а двойственное несчетное мерное. Если несчетное мерное берем, то двойственное будет иметь еще больше кардинал базиса. Вот. И да, и поэтому вот тот же феномен имеет место в общем случае.
Я слышал, я прочитал еще какое-то рассуждение, которое мне тоже не совсем было понятно, про то, что типа как-то это связано с тем, что из прямой суммы до гомологии можно получить прямое произведение, а обратно нельзя.
Но это и есть прямая сумма, это и есть конечная линия комбинации. Вот здесь действительно вот это прямая сумма к гомологии точки, это прямое произведение к гомологии точки. Ну, z это
Если прямая сумма еще понятно, почему это прямое произведение? Наверное.
Ну, а что такое прямое произведение? Это мы взяли по одному элементу в каждой группе.
Ну, то есть, в чем отличие?
Прямая сумма это конечная комбинация, прямое произведение это произвольная комбинация. Нет, это просто определение.
Я не знаю.
получается вернуться, потому что если вы берете двойственную вот это, вы получаете что-то гораздо больше.
Ну да, проблема.
Вот если вот этот пример с Z продумать, то это как раз очень...
Ну значит, я сейчас неправильно утверждение сказал, не совсем двойственно, но как бы там есть двойственные
Нет,
соотношения.
двойственным пространством называется то, которое холм из нашего пространства
Да.
в поле. Вот в одну сторону двойственность есть, вот это двойственное.
Да.
Ну, просто слово двойственное не очень хорошее, потому что дважды двойственное не возвращает нас туда же. Вот.
Спасибо. Не, интересно.
Это вот такая вот типичная бесконечно-мерная проблема.
Сейчас проблемы, которые у нас были сейчас, которые могут возникнуть за это только поручение, потому что некоторые свойства у нас не будут выполняться.
Да, причем, это некоторая вещь, которую, как бы она за рамками нашего спецкурса, но возникает только два поручения.
Два поручения,
То есть вот на 2 все умножить, все будет выполняться. Но это надо более аккуратно показывать. Но вот это настоящее целое число. Здесь не возникает никакого для этого.
понятно, да. А есть ли какие-то преимущества тогда рассматривать теорию другими теории космологии?
Нет, так есть, конечно, все это имеет в гвардизмах аналоги вести.
Просто если свойства буквально практически одни и те же, то в чем как бы выбирать какую-то одну теорию?
Нет, свойства не совсем одни и те же. Нет, мы сейчас экстраординарные теории не обсуждали, свойства немножко другие.
Понятно, да. А можно вас задействовать на следующей неделе, вот, поздавать задачки и еще обсудить немножко из статьи, которые вы дали почитать? Там
Так, у вас телефон мой есть?
есть.
Значит, до пары можете в четверг? Потому что после я не могу, после я сразу должен быть.
Да.
Вот. Давайте созвонимся где-нибудь там в районе среды. Звоните на пункт, а то я до четверга забуду.
Да.
Вот, чтобы мы до пары встретились.
Да.
Прошу.